Okay, so I'm going to talk about today DALL-E and CLIP. So DALL-E is where the whole revolution started on, generating realistic images from giving the prompt like a caption. And CLIP is also very important contribution, which really impacted DALL-E 2 and all other image generation and video generation, or even the other problems in computer vision. So these are very basic papers, and they're very recent. So I will cover these at the high level quickly so that you have basic understanding. So if you want to understand detail, we actually covered these two papers in detail last year, and we have a whole 30 minutes presentation on the website, so you can look at that also. Okay, so DALL-E is a paper in ICML in 2021, and this was presented by these students last year, and this is a YouTube video out there. So it generates images from text captions, and it's a 12 billion parameters version of GPT-3. So as you know, this GPT is very impactful these days. You are hearing a lot about GPTs, right? So ChatGPTs, there's so many articles these days in the media. So that GPT, as I talked about the first lecture, is a generative model for text and uses transformer and so on. So, so this uses a data set of 3.3 million text and image pairs, and it can combine unrelated concepts. For example, it can generate these images, an armchair in the shape of an avocado, an armchair imitating an avocado, and so on. So people are very surprised that you can do that. So there are some more examples. Here's a taper made of an accordion. This is an illustration of baby hedgehog in a Christmas sweater walking dog, and so on. Neon sign that reads backprop, and then exact same kid on the top as a sketch on the bottom. So now this work, of course, is built upon the other work, and we have touched upon in the previous lecture, but we'll go through again. So one concept is called autoencoder, okay, which is encoder and decoder. Other is called variation autoencoder, which is a continuous state space. And then the third one is called the discrete quantized state space, which is the vector quantized variation autoencoder. And the DALL-E is built upon VQVA. So autoencoder, I think everybody knows that, we have encoder, decoder. We take an image, we encode this. This is just a neural network, and we get this latent vector called Z. And that Z go to decoder and give you the image back. So we reconstruct the image, and we train this by looking at the difference between the input image and the reconstruct image. We keep iterating and find these weights for these encoder decoder. So now what the problem with the autoencoder is that there are some gaps in the latent vector. So let's say we take the latent vector, which is a typically high dimensional vector, 512 dimension or more. We just reduce it 2 dimension, Disney. So these are different classes. These are samples of some data set, which is shown here, cartoon set. These are the samples from that, and this one class, this another class, and so on. So there are gaps, and that's a problem. Okay, so to fill this gap, so there is another one which is called variation autoencoder, or VAE. So here, not only we will given an image, we will not really come up with a latent vector, but we come up with this distribution, which will be more general, and which will be the mean and variance of distribution. And then we are going to take the normal distribution, standard distribution, a bell curve as you are familiar with, and sample from there. We will add that, multiply that with the standard deviation and add with the mean, and that will become Z as compared to what we are estimating. In autoencoder, we are just getting the latent vector directly, but here we are estimating this thing. And then we will sample from this and give it to decoder, and that will be better as compared to just simple autoencoder. So this will be VAE, so it will fill in the gaps and it will give us better as compared to this one. These are different classes, okay? Now, still people found out that there is problem with the variation autoencoder. And so here is the example. So here we have, these objects, we have a triangle, we have this square and so on. And this is showing you the latent space distribution of these. So, so it is regularized. We want to vector sample from latent space can generate a valid data, but when they overlap the distribution, then they can morph into different data. So here's an example. As you see, the orange ball is moving through different classes, and when it's going to triangle, it's generating triangle and circle. But then when it is going between like triangle and rectangle, then it's generating like a trapezoid or something. So that is, like this one. So this is the morphed image, and that was not, was not the intention, not the object which we generated. So because it's a continuous space, so variation autoencoder. So now to fix that, what is called the vector quantized variation autoencoder. So what we are going to do, instead of having this continuous space, we are going to quantize this latent space, and that will kind of fix this problem. So this is VAE. So we have an image, we apply it to encoder, CNN. We get this tensor, the feature matrix. So each of this is some dimensional vector. And so typically we'll get encoder, we'll go to decoder like this. But now what we are going to do is we will have this code book. These are, the vectors. And we want to take each of these latent representation or encoded representation of each of these and attach to one of those discrete code. We don't want to have any number. So we want to say, well, this is similar to what code, and we'll assign that code. So it'll be approximation, but it'll be quantization. So as you are familiar, quantization, you take these numbers and quantize, say 4 levels, 8 levels, and that's what's happening. So here's an example. So let's say we have this one of this latent vector from the encoder. So we will look at distance from here to all other codes. These are the codes. So this is similar to E2, and we will assign E2 code to this vector, this feature vector, as compared to using as it is, as we are using in the VAE. So that's a basic idea of VAE. And that is what is used in the DALL-E. So now we are going to go to DALL-E in detail. Now DALL-E is again transformer to model text and image tokens as a single stream of data. And it has 2-stage training. And so first stage is basically autoencoder. Okay, so we take an image and we do the CNN encoder, we get these features, and we will do the discrete autoencoder quantized VQA, as I explained here. So instead of sticking to one of the code, here we'll have distribution, and I'm going to explain that. So we'll get that, and then we will now have these feature vectors in terms of this codebook, and then we'll go to decoder and get reconstruction. So that's a stage one, okay? And we'll go in detail. So then stage two, we will have prompt. We'll have the text, because we are given a text, we want to generate the image. So this is the text encoding, and this is the image encodings, and this will go to transformer. Again, we will get a distribution, and the transformer will output one code, one token at a time for the image. And we'll generate this cube, and that will go to decoder and will generate an image. So that's the kind of two stages. Okay, so let's go a little bit more detail. So stage one. So stage one, we will want to learn the visual codebook. So it's a discrete variation autoencoder, and it's similar to VQE, VQVAE, but it is using distribution instead of nearest neighbor, as we are explaining, that we take this latent vector and we'll come up with the E2 was the closest one, and we pick that one. But here we'll have distribution for the all code words. So now, so let's look at this again. So that's what we have, as I explained before. So that we take an image with the encoder, we get this feature tensor, then each of these token will get distribution, and we'll do the softmax, and then we'll multiply with this codebook, and we'll have a quantized feature representation compared to this one, and then we'll go to decoder. Okay, so let's look at some example. So let's say we have an image, we have a caption, we have prompt, and image is fed to the encoder network. That's a first step. So first we take an image and we feed to the network, encoder. And this is just a simple example. It can be anything, and we haven't talked about is it actually a transformer. So we get this representation, and let's say just for this example, we have only 4 codes. Okay, our codebook is only four words, 4 codes. So we are going to find out this particular image. What is the probability that it belongs to the code word 0, code word 1, and so on. So these are numbers. So we get a distribution. So as you see, that is high probability is code word 2, and lowest is code word 3. So we'll get the distribution. So you will realize that the generative model distribution, or even in general deep learning, distribution is used again and again, and that's a pretty nice concept, and you want to be clear about that. So that is and let's say another latent vector after the coding is this one. Again, we have 4 latent vector, 4 codes, and these are probability for that. So this is the latent vector, 1, that's a distribution of that. This is the distribution of latent vector 2. This distribution is in terms of the code words. And these are the code words or code vectors. So 4 code, and these are, can be as long as you want. Okay, so that is the first concept. Now we will take these probabilities. We will do the softmax so that they can sum to 1. Okay, so this, as you see now, this has the highest 0.95. And then we'll take this multiply with our code words, and then it will go to decoder. So feed the resultant vector decoder, network to reconstruct. So the basic idea is simple. It's basically autoencoder. We take an image, get its features cube, and then we want to avoid these problems we talk about, that we'll get a morph image and so on, to stick to the code, discrete code, as compared to having just general Latin vector. But then on the top of it, we don't want just discrete code, we want a distribution, that it should not be only to one of the code, but it can be a distribution for all these codes. And then it just go to the decoder. So that is basically stage one. Now let's look at stage two. So what we are going to do now, we want to predict the distribution for a next token, okay? And then we'll do the, next token, and so on. We'll go through all, in an image, we'll have 1,024 tokens. So we'll do one at a time. And this was the idea here, that this is a prompt, this is the text encoder, it's a transformer. Transformer, again, same thing as we talk about. That's why I wanted to cover transformer. Transformer has the self-attention, feed-forward network, and multi-head and multiple layers and all these things. So right now it's just a block. So you understand that. So what it will give output will give you the distribution of the one token at a time. So now this is a token, image token. So that will go here. Now this will also be fed back to the transformer. Okay, so that's called, it's called auto-regressive. You compute one token, then based on that, we compute the next token, and so on. Let's keep going. So here, once we finish all 1,024 tokens, then we just give it to decoder and we get an image. That's it. So that's basically stage two, and a pretty innovative way to generate an image from the text. Now, as you see that we are just given the text prompt, we are getting an image. Okay, so it's a transformer. So we'll encode the lowercase caption into 256 text token, maximum description 256. Even if it's a large, we just shrink it, crop it. And then vocabulary size they use over 16,384. And the 32 by 32 image tokens, and their vocabulary size about 8,192. And there was 64 attention layers, okay? And each one has 62 attention heads. So this is a pretty heavy transformer. And there were 12 billion parameters. So training was done on the Wikipedia images and YFCCA 100 million plus dataset. And they removed some of the images, small captions, non-English dates, extreme aspect ratios, and so on. Now, testing was done on the MS Coco, and this is about 328,000 images. And this is used, it's a standard data set for computer vision, object detection, segmentation, key point detection, captioning, and so on. And then second data set was CUB, and this is 200 bird species and about 11,788 images. So, so these are some examples. So a very cute cat lying by a big bike. So this is their generation, and these are the other gain-based approaches. And this is a China Airlines plane on the ground at an airport with baggage cars nearby. This is their image, and these are the gain-based, and so on. So now they can generate many of these samples. So they have a way to select what's a good sample. So this was group of urinals is near the tree, and they generated 412 different samples and selected based on that. Now, if you have just one, then it's not that good, and it's getting better when 64 and so on. And similarly, crowd of people standing on the top of beach. Now, here is from the 512 samples, but then here will be less than that. So more examples here. A woman and a man standing next to a bush bench. This is only one sample, but when you increase the samples, then you get better results. Now, to determine which image is, good, better, one of the metric they use is clip, and that's what we're going to talk about next. So this is a pre-trained contrastive model, and it will rank the DALL-E's generated images. So you have caption and you have an image, so you're embedding for those and look at how similar they are. And so input is image plus caption, and will give you output score, more images to rank, better quality of best. Okay, so that's about DALL-E. So let me now go through the clip.
Professor?
Yes.
I have a question. So how do they ensure that the model outputs a novel image and not just outputs the images that it was trained on?
Yeah, so I mean, they have lots of lots of these examples, and they have a vocabulary of these text prompt, and they are learning. So any learning-based method, is basically using that idea, right? So you have represented data set and corresponding image pairs, image and text pair. So once you learn, then you can have any particular prompt and it will generate an image. And of course, some of these images were not realistic, so that's what they have evaluation. But it's that's the way it is. You give some correct pairing, and you go through the process and minimize the errors. You learn all these parameters, and then after that, you evaluate how good you are doing.
I have a question as well.
Yes.
Is there any quantitative way to measure how good the generator generates the image?
Yeah. So there are lots of other methods. One is called the FT measure. There's the inception score, and there are many other measure to generate these gain images. But the main thing here is that those metrics are used for the image generated by GAIN, and GAIN not necessarily has the text prompt. So the DALL-E and these other methods, which we're going to talk about, diffusion model and so on, there you have a text also. So yeah, you're right that there are these all other methods, and even you can have the humans in this paper. They talk about, they show the humans. They say, well, this is a text, this image. You rate it, how good it is, and that there are many metrics. Okay, and we will discuss those as we learn the papers. Okay, so let's go through the clip, and this is also a very nice paper. So this was in 2021. They already have 3,000 citations, and again, this is from the OpenAI, and these were the students presented this paper last year, and the video is available on YouTube on our class website last year. Okay, so it's called CLIP, Contrastive Language Image Pre-Training. So this is a mechanism for natural language supervision. And again, we are going to use a pair and image with its caption, and we'll use a contrastive learning. So, and it beats the fully supervised learning baseline on many data sets, which is very surprising. I'm going to give you examples. So, and it can be used also as a zero-shot classifier, and I'm going to explain what we mean by that. Okay, so what is CLIP? So idea is very simple, which is, very impressive. And as you know, in science, at the end, the good science is, it's so simple, and people think about, how I didn't come up with this idea, when you know. So that's the beauty of good science. So here is the idea. So we have caption, paper, the Aussie pup, and this is the image corresponding to that. And so we do encoding of text, we do the encoding of image. So let's say, we get the T1 text encoding, we get I1 image encoding. Now we will have in the batch, we will have several images and several corresponding the text prompt. So we will have these text encoded. Suppose we have n number of image pairs. So we'll have their encoding and there'll be their encoding. So what we are going to do, we will look at the cosine similarity between each of this pair. So I1 with T1, I1 with T2, I1 with T3, and I1 with Tn. So, and then we take an image 2, and again, cosine similarity with all other texts and so on. So we'll get this matrix. Now, as you know, that the first image is paired with the first text. So this similarity has to be very high. Similarity second with second text is high. So now the diagonal, this has to be very high, and this off diagonal has to be low because it's different. It's a wrong caption for the image. So that's the idea. So we want to learn the text encoder and image encoder such that this is maximized and the rest of them are minimized. Very simple. Okay, so that's the first step. That's a major step. Then we have the zero-shot learning, zero-shot, detection or prediction. So now we learn the text encoder and image encoder. Now we want to use it. So, and we want to use it for completely different data set, which we haven't used for training. And that's why it's called zero shot. We have zero example for that particular data set. So what we are going to do is, let's say we have some data set which you have plane, car, dog, and so on. So these are the classes typically, we are used to. So we'll take these class labels and convert them in a sentence. And simply they did just say photo of a plane, photo of a car, that's it. So because this is a caption, this is a text, because this is where we learn the text encoding. So we are going to use this text encoding, like that, okay? So now this is the data set we haven't used. It's a new data set, and we are going to test our text encoder and image encoder. We are going to use that to classify that data set without any training. Okay, so now with that, a photo of car and whatever object is, we get this, and then now during the testing, we get an image, we do the image encoding, and since we have all these classes in our data set, the testing data set, we have already encoded them in the text. So let's say we have n classes, so we just compare the text encoding or class 1 with the image encoding, and text encoding image class 2 with image encoding, whichever give us the best match, we say that is a class. So that's it, very simple. And that, made a big difference. So that is basically called zero-shot prediction. So the whole thing is that we are leveraging these text encoder and image encoder. Okay, so zero shot is much more robust. So it can be applied to the ImageNet data set, and it actually give you better, close to the supervised ImageNet. We train a ResNet network, and we get 76.2, and here zero shot. We haven't trained the network on ImageNet at all. It gives you same performance. Similarly, ImageNet version 2, it actually give you better, 70.1. ImageNet's penetration, ObjectNet, huge improvement, 72%. And ImageNet Sketch, again, a big improvement, So that was really shocking. Okay, same thing, imaginary adversarial. It's a 77%. It works pretty well. So motivation is that now, as you know, in machine learning, we train a classifier on limited number of classes. For data set, it works, which is good. But when we change the different data set, it doesn't work because we don't know those classes. So that's a big problem. So you want to resolve that. So in this traditional formulation, we have fixed number of labels, and we cannot do generalization. So with CLIPS, we want to overcome these limitations, and we will use this contrastive learning. So classification tasks, normally you train this network, you have an image and you have these different layers and so on, and you come up with the output. And here we have 10 classes in MNIST, and you minimize a loss and you learn these things. But we have, for each of these, we have a label. It's a supervised classification. Okay. Now, contrastive learning, what we're going to do, that we have a positive sample and we have a negative sample. So we have an anchor, and we have a positive, and we have a negative. So we want to learn this representation such that the positive comes close to anchor and the negative goes away. So that's the idea of this contrastive learning. So very simple. And this can be done without any labels. So it's used a lot in self-supervised learning. So now what is zero-shot learning? So we want to train on one data set and generalize on unseen categories. Okay, so here is an example. So let's say we have these classes, the horse, boat, dog, and we train it. And of course, we can take these, it will work for these. But now we haven't trained on these other classes, jet ski or donkey. And so these are the unseen classes. So we want to be able to do that, and that's what zero-shot learning can do it. Okay. So so they use this WeblmageText Dataset, and they collected their own. And because they say YFCC 100 million is not enough, and they search the image and text pairs and 500,000 text queries and use for pre-training CLIP, and they were looking at 400 million images. And so the idea is that I think this slide should be not there. Let me go to the right one. I thought I fixed this one. Just hold on a second. Where is it? Maybe it did not. Let's try to do this thing here. Okay, good. I hope it didn't change all of those. Okay, so what we have is the input image, and we have a caption, dog lying in grass. So what we are going to do, we'll encode the input image. Let's say this is represent the HI, it's a vector. And then we'll encode the text, which is HT, which is text representation. And we want to maximize, because this is the right caption for this. And so we will maximize, we will take the cosine similarity between HI and HT and normalize it, and we want to maximize. Okay. So let's look at another pair. We have input image, and we have which is input image of airplane, and we have a caption dog lying in the grass, which is incorrect. Okay, so again, we will image representation, text representation, and we want to minimize because they are different. So that's why we'll minimize that. So that's basically the contrastive learning. So this dissimilar images, earlier one was similar images. So what we are going to do is we'll take the input text, we will do encoding, and this will be the input to the transformer. We have 12 layers, 112 with 8 heads. This is end of sentence and start of sentence. After that, we'll come up with the output representation from transformer, and then we will linear projection, and we will have text feature representation. Similarly, we will have the image, again the transformer VIT we are going to use, and then we will have the CLS token, and then we will have image feature representation. So that's it. So they also use actually Resonate, but they found out the VIT is better, the transformer is better. Okay, so how do we do clip pre-training? So we have the caption, and we have an image, and text encoding T1 to Tn, because we have n encode batch of text, and batch we have n pairs. And similarly, we have the n images, we get n encoding, and then we want to maximize the cosine similarity between correct matches, which is this one, and minimize the this animation, minimize the cosine similarity between incorrect matches. So now let's try to understand how we come up with these loss functions. Okay, so these are the text encoding, and these are the image encoding, and in the batch we have n samples. So what we're going to do, we will represent mi as a 1-hot encoded label vector for the ith image. Okay, so like this one. So we'll take the on the ith, in this case 3, we'll put a 1 there, and rest of them 0. This is called 1-hot encoded. Very simple, because we know this is the image, and that give you all that can consider as a distribution. So then we will have the cosine similarity vector for ith image. So that is the cosine similarity of the ith image. So that is similarity of the text encoding of 1, text encoding 2, and text encoding 3, and so on, as is shown here. So this is the cosine similarity, because dot product normalized. So that we will represent ym, and this one is mi. So now we have these two vectors. One vector is 1-hot encoded, which has only 1 at the 3, and the other vector all 0, and the other vector is a cosine similarity between an image with all other text. So those are two vectors are distribution. Then we will do the same thing for the text. We'll come up with the 1-hot encoded of this particular text. So we'll put the T3 third element with 1, all with 0, and then we will have the cosine similarity vector with ith text sample, which will be a column. So same thing. So we'll take the T3 and look at similarity between I1, I2, I3, I4 up to In. So again, we'll get this vector. So, and both are distribution. So one distribution is from the image to, which is mi, 1-hot encoded distribution, and ym, which is cosine similarity vector of ith image with the text, and other is the column wise for the text with the images. So then that's it. So we will look at the cross entropy between these two. and cross entropy between these two. So we'll add up those losses. So that one, this is the cross entropy of the MI with the YI. And this was just one I3. We'll do the I1, we'll do I2, I4 up to IN. So that's why the summation is from 1 to n. And we divide by n. So then we'll do with the text one like this. And this will be the YIT and TI. And again, we'll do all the text one from T1 to Tn. And we'll add up and divide by 2. So that's a loss function. They train this clip. It's pretty nice, very simple. And basically, we are learning the image encoder and the text encoder. That's it. Okay, so these are details. So training, they did on 400 million images, text pairs. So they use a huge batch size of 32,000. That's a problem because they need to. That's why they need to use a lot of powerful GPUs, and they have these mini epochs, and they have decade and architecture. They try the ResNet and VIT and transform-based text encoder. So testing now, once you learn, so you can do two things. One is to use those features to do classifier in terms of the supervised classify. Other, you can do zero-shot learning. So first one is a linear probe, and other one is zero-shot prediction. So let's talk about linear probe. So we get these features, and we can use those features to train any classifier on any data set. And this supervised classifier, so we can see how well that works. So that is the first application of this. So they use this data set, the standard, this combination of 12 different data set, food, CFAR 10, CFAR 100, sun, and all those things. And these are number of classes and size and so on. And they also extended this data set. They added more 24 other data set, and then this they tested on this also. And they found out that this works pretty well. So here is the accuracy, and these are the different methods. Of course, the red one is theirs. One is clip VIT with transformer, other one is ResNet. And these are other networks, EfficientNet, Sinclair, MoCo, these are all sorts of based method, ResNet, and so on. So as you see that this clip one beats everybody. But one thing is that this clip is transformer based. This is a ResNet based, so transformer works better. So these are the other methods, and this is how much time you want to spend in training forward pass, how much time it takes. So on this 12 dataset evaluation suite, standard, it works. Clip ResNet-based model underperforms, and VIT-based clip outperforms everything. And this is the extended dataset. Again, clip perform beat all other methods, and then both versions, even the transformer and ResNet-based method, and then gap increases if you increase this computation power. So then this one is that you can maybe don't use all the samples as we did before in these examples of this 12 dataset and 27 dataset, but use few examples. So it's called few shot learning, a low shot. So again, in that case, they are showing here 0 to 16 shots. Again, the clip does pretty well compared to these other methods, so which is good. Clip scales well, and linear probe clip climbs, ResNet other methods flatten. And zero shot clip outperforms non-clip to 16 shot. Okay, so now again, let's look at, so that was the supervised. So we have these in labels and we just use the features we learn from clip. Now we are going to do actually zero-shot learning, which is pretty interesting. So as I explained earlier, so we will take the classes and we will convert each class name to the sentence and use a text encoding. And then given a query image, we'll get image features and find out these cosine similarity, whichever class it gives you, that's the answer. That's it. Very simple. So for that one, they do very well. So on these data sets, the zero-shot clip, while supervised, which is a linear probe supervised method, they all outperform 28%, 23%, 22%, and so on, which is pretty impressive. And then so they also use the video UCA 101 and Connectic. So here is some more examples. Now in this one, they don't perform that well. They actually perform less, which is negative here, as you see. So underperforms on many other data sets, mostly on specialized complex data set, and like satellite images, tumor classification. And so zero-shot clip is highly generalized. Okay, but not suited for hyper-specific task unless fine-tuned. Okay, so that is the end of the